let's look at kinetic energy. So we've been talking about torque, and then of course rotational motion, and the effects of the moment of inertia on motion. So what about kinetic energy? Now, we talked about kinetic and potential energy as far as Newton's laws, what we call Newtonian motion, and then of course this is still Newtonian motion, okay? It's just not only linear that we're looking at and considering, we are also considering rotational too. So if we take, and by the way, these come by the same way that we derived kinetic energy. If you take Newton's second law and integrate it, we come to kinetic energy. So these come also by integration. So we could take these, we could start with rotational motion and integrate, and start with moment of inertia and integrate and come to these equations, okay? All right, so we look at kinetic energy, and this is total kinetic energy of a body that is rotating about an axis. Now notice there are two parts to this, okay? So K total, they didn't put total there, of course, is 1/2 the total mass times the velocity center of mass. It's a little bit different than linear velocity, a little bit, okay? It's the velocity center of mass. And remember how we solved that from momentum centimeter of mass. Remember that? Okay. So we're looking at velocity center of mass plus, and notice it's 1/2 just like it is in regular kinetic energy, linear kinetic energy, 1/2 the moment of the inertia center of mass times the angular velocity squared, okay? So we have rotational, rotational motion and translational motion. Okay, now if we look at this, part right here, this is our translational, and this part right here would be our rotational, right? And this is broken down for you, or annotated for you on page 310. Okay. So this is our rotational. Lord, I can't spell this morning. All right. Rotational motion. Okay. Now again, what do we mean by translational? If you've ever watched a wheel as it moves across the surface, if you watch the wheels in this stroller, okay, or cart. Good Lord have mercy, chair. Not a stroller. Thinking about my kids, I guess. This chair, you notice that it not only is spinning, but it's also moving in a linear fashion, okay? We call that translational motion, okay? Translational motion. Now, why do we just not use linear? Well, because we have an object that's rolling across a surface, okay? It's not just like we're pushing something, or we're just talking about the speed of a car down the highway, okay? We're actually now applying how that object rotates across a surface, okay? If you've ever looked at the gears in a machine, you ever noticed how they're different diameters? You ever noticed on your bicycle how the spoke, the rear and front spoke, has different diameters, okay? That's for a reason, okay? It's not only for reasons of mechanical advantage, but it's also for kinetic energy reasons, and when you look at that, you also look at its velocity, its translational velocity. If you want something to turn slow, typically you have the main gear geared into a what? Like your gear from your motor or your gear from your crankshaft. If you want it to just move real slow, you have your main gear hooked into a very large gear, don't you? Well, why is that? Why will it move slow? Because you have a very large circumference. You have a very large perimeter through which that gear has to move. And especially if your gear from your motor is small, even though it may be turning fast, you can still move slow. Likewise, if you want to start picking up speed, look at a 10-speed bicycle or a 5-speed or whatever it is. Notice how as you go down in the sprockets, as they get smaller, you get faster, don't you? But it's harder to pedal too. Okay, it's a lot harder to pedal. Okay, that's why typically you don't start shifting gears till you get on up till you top out, and then you shift into a higher gear, and then you can go faster, and then you shift into higher, and it's not as hard because the momentum of the bike helps you, doesn't it? Sure it does. Okay, so translational, like I said, is like a wheel turning. Okay, there's the spokes. A wheel's turning. Let's say it's rotating clockwise as it's moving in this direction. So the translational velocity is this velocity here. And the rotational velocity, of course, is the actual motion of the wheel. Okay. So we have two kinetic energies, not just one. Oh shoot. Okay, we have two kinetic, and it's real easy, y'all. We just add them up. We want to know the total kinetic energy. Because remember, as that wheel spins, y'all, it has that moment. Remember, y'all, there's a moment there that's created by the motion. And so that produces energy too. I talked about this the other day, how when an object starts to spin, you know, that outside force typically has to be greater to stop it. Okay, because why? Well, because once you get it to moving, you've got to take into consideration the moment of the device. Not just its translational velocity, but its rotational velocity too. Okay, because it has mass. Okay, and so there's energy there. Okay, so that's a very easy equation. Now, please note now, notice that says I. And how many I equations did I give you? And by the way, I gave you a handout. This handout, I would like for you to look over it. I'm probably going to give you another one just like this one. Or if you want to, you can bring this one back on final day. Just make sure you don't write no notes, okay? I mean, I know it's got formulas and stuff on it, and you're not going to write no notes. I mean, what I say with that is, these might be a little hard to read. You can correct them if you need to, and that's fine. I don't care, okay? So, you know, you can, like some of these equations are a little bit hard to read, and y'all did the best I could. The printer printed, it just printed, okay? Did the best it could. So you might want to go back and look at them and write them a little bit more clear, especially some of these on moment of inertia, okay? So we've got what? We've got 8 moment of inertia equations there based on the size and the shape, and where the axis of rotation is will determine what equation we use, okay? All right, so don't forget that. When you see I, okay, that could be a number of different equations, and of course you would need to substitute in and solve, all right? So here they're talking about the rotational aspect and the translational aspect. That's a little bit harder to understand, this motion here. I don't really see the rotation there in that motion there. That's not a good way to demonstrate. I'd just say take a wheel and move it across the page. That'd be the best way to me, but anyway, I didn't write the book, okay? All right, now what about rolling without slipping? Of course, again, this translational motion, it's very important we understand that in order to have effective translational motion, you don't want it to slip. Okay? You don't want it to spin out. Okay? You want it to get traction. And so as long as we have good traction, then we can simply find and again, that's the velocity center of mass, by taking the radius of the wheel and multiplying it by the angular velocity, okay? And of course, we will get meters per second, okay? Meters per second, because we got meters times radians per second gives us meters per second, okay? So provided it's not slipping, this is how we solve, can solve for an object with translational velocity. Okay, there's another equation. Real simple equation. Okay, real simple. Okay, and here they show you the dragster doing the burnout. Now I know there's a reason for that, but you got to realize that thanks to the spinning of the wheel and the slippage of the wheel, you cannot find the velocity center of mass will not be equal to. Because now what has happened? Well, you're not moving. Okay. You're not moving. It's just sitting there spinning. It's just, okay. So it cannot be equal to the radius times the angular velocity. Okay. Okay. Actually, there really wouldn't be any translational while it's sitting there spinning. Okay. Not much anyway. You could have a very high spin rate, but you've ever noticed you really don't start getting much energy behind the vehicle until it gets traction and moves on down the road, right? So if you think about it, just because you do a burnout, even though it'll help you get traction, and that's why they do it, you're not moving. Okay. Basically, there's very little energy. Okay. And that's what you need. You need high energy so you can have a high velocity. Get down that track. And remember, the relationship of the velocity to the energy is squared. So if you double your velocity, you quadruple your energy. Okay? All right. Okay? And so we can then take translational and rotational dynamics, and of course, this is not going to change, Newton's second law, and we can find the torque. I think we've already seen this equation where we take the moment of inertia of a rigid body, and the key there, rigid, okay, rigid body, times the angular acceleration. And of course, the units for torque, what are the units for torque? All right, so units for torque, make sure you did get this the other day, is a Newton meter. That's the units for torque, okay? Now, we're not talking about work, because I thought a Newton meter was a joule. Well, it is when the device or when the object is moving through a distance. But here we're just talking about torque, okay? You can torque something and it not actually, let me see if I can say this right, there's really not work done on it, okay? Basically what you're doing, what does torque mean? Remember what we said torque was. It's the tendency of an object, the tendency of an external force to either do what? Create or stop motion, typically rotational. So if I apply torque to something, okay, even though the bolt may not be moving in the X direction or Y direction, I'm applying a force through a given distance, okay, called the lever arm. And so I create something called torque. It's similar to work, but it's not exactly the same thing as work, okay? Because as we get to a little bit later, you'll see that we can find work by taking the torque and multiplying it by the angular change in angular displacement, okay? All right, so we can find the work that way. Okay, so please make sure you understand units for torque is a Newton meter. All right. Now, it's pretty unique. Provided there's no friction, we can actually ignore it if it's rolling over a perfectly rigid surface. For example, the wheels rolling across the floor on these chairs. We can almost ignore the friction there. There's very little friction. Okay, very little friction because both are rigid surfaces. Cars on the pavement. That depends. If you get like a semi on pavement, you ever watched a semi as it eases up to a red light? You ever watched the pavement, the edge of the pavement? It'll compress, won't it? I remember one time I was watching a cement truck get ready to, it pulled up by the edge of the pavement. It was going to back into the yard, and man, as it come by the edge of the pavement, I mean, I could not believe how much it compressed the pavement. It was on a street, it wasn't on a highway. So streets, they don't have as much. But it was loaded down, I forget how many yards of concrete. So yeah, it really, so there you would have friction. Okay, you would have considerable friction because it deforms the pavement, and then you got the tire gripping to both sides of the pavement. Okay, which is okay. I mean, you want traction, but you have more friction there. On concrete, however, you know, if the wheels are hard wheels, now rubber wheels, they're going to compress. We know that. So there's going to be friction. But if they're hard wheels, you know, if it's a hard, rigid body on a hard, rigid surface, you got very little friction. Very little friction. Now, you know, if we're using let's say a dolly to move equipment around in the shop, well, that's what you want. You want that. But if we're trying to get traction, you know, we wouldn't want to drive vehicles with hard tires. That just wouldn't work. It would be really, first of all, it would be very unpleasant ride. You'd have to have one more shock system. And another, too, you know, it would be hard to start from a stop because those hard surfaces against each other are going to slip very easily. Okay, so you wouldn't want that. Back in the 40s, right around the beginning of World War II, the government had to make tires out of hardwood. There was a shortage of rubber. And some of the wheels on the tires on their trucks and Jeeps, especially trucks, they actually were made from hardwood. There was such a shortage of rubber because when Japan invaded Indonesia, they took over. They already had control of most of the eucalyptus plantations, and you know, back then it was still made from natural rubber, and so there was no more natural rubber. So the government had to make hardwood tires. It was crazy looking. You can go Google that and find it. But so they had to really, if you remember your American history, there was a rubber drive. My dad remembers when he was a kid, we'd get out in the woods and everything, run to walk the ditch banks and stuff along the road, and we had old shoes. We could go turn them in and get, you know, they'd give you a little money, not much. But they were recycling that rubber. They wanted all your rubber tires, inner tubes, soles off shoes. Why? Well, because we didn't have natural rubber to make tires with. And fortunately, I think it was DuPont. Discovered a synthetic way, because it came right along with about the time nylon was discovered. They discovered a way to make synthetic rubber. And man, you're talking about a push to start building synthetic rubber plants. They built about 4 in about 3 years, I think, 2 or 3 years. They had to, because we had to have it for the war effort. So, and it was in the late 30s when they discovered synthetic rubber, or 1940. So yeah, it come just at the right time. I think by 42 we were able to produce enough rubber to supply the war effort, but you couldn't buy tires at a tire store hardly. You couldn't buy cars. It all went to the war effort. So anyway, so just thought I'd throw that out there, a little historical tidbit. But yeah, they actually made hardwood tires. Anyway, I guess it was something to keep the rim off the pavement. Of course, they wouldn't last long. You know, they wouldn't last long, and I'm sure traction was horrible. Okay, so what about work in rotational motion, as I mentioned earlier? Now look, notice we take torque. Remember, the units for torque is a Newton meter, but you said, well, wait a minute, that's not work. Remember, y'all, it has to move through it has to be displaced, okay? It has to be displaced. So when we look at work in rotational motion, we have to consider the angular displacement in radians, okay? So when you torque a bolt, are you actually doing work on it? Yes. Okay. Because that bolt does what? It turns through angular displacement, doesn't it? Sure it does. Okay? Sure it does. All right. Okay. So, and notice it is the integral, but now what if it's now please understand, this of course is if we, and again, you can solve it either way, whether the force or torque is constant or non-constant. You can solve it with an integral. But if it's constant, then we can find the work by doing what? It's the torque times what? Change in theta, right? Because that D represents, we know that you integrate, which means change, in a sense means change in, okay? We know it's the area under the curve, we know that, okay? But in a sense, it's the change in, because what is the area under the curve? Well, it's the change in motion, okay? All right, the displacement, all right? And so we get joules. Of course, you know the unit is the joule. That's always going to be the unit for work. It's always going to be the joule. That's not going to change. Same thing for energy. So you see the little girl here. She's spinning the merry-go-round. She's applying, and notice too now, tangential force. And so how can we find torque that way? Well, if you remember, torque can also be found force through a radius. a force applied across a given radius, okay, the product of the force and the radius. And so we can find torque that way. So we could find the force here, the radius of the merry-go-round, and find the torque, and then the angular displacement, and find the work. Okay? So please don't forget we can find torque this way. Okay? All right? All right. Now what about power? Well, guess what? Same thing applies. And this is one way to find power. There's one way we can find power. So when we look at power in rotational motion, well, y'all, would it not make sense that it is the what? We can do it two ways. The torque times the angular velocity will give us power. You've got a Newton meter times a radian per second. And so a Newton meter is a what? Is a joule, right? And a joule divided by a second is a watt. So if we know the torque and we know the angular velocity, we can find it this way. Okay. Just remember your units, okay? Or we can do what? If we know the work divided by what? The change in time. And how can we find work? Well, we can find work by doing what? The torque times what? The change in angular displacement, right? Yeah. Okay? So a couple of ways to find power. That doesn't change. The unit's the same, still the watt. Okay. If you think about the helicopter blade as it rotates, think about how much power you got to have to keep that thing off the ground. And two, think about the torque that's being created. That's why, and the angular momentum, as we're going to get to, that's being created. And that's why helicopters have to have the rear rotor, the vertical rear rotor. You've got a horizontal rotor. Well, without it, if you've ever seen any old footage of some of the first helicopters, they didn't think about the rotor needing to be on there. And what did they do? They just spun around and around and around, which is Newton's third law, y'all. If you think about the motion, with every action, there's an equal and opposite reaction. So they should have thought about Newton's laws and thought, well, we got to have something to counter that. We got to have something to equalize or balance that opposite force. And so they used the small rotor. That's why the easiest way to take a helicopter down, if you're in war, is shoot the rotor out. One of the easiest ways. You can shoot that now. I'm sure it would be hard. I've never done it. My brother's talked about it. He said my brother was military and that they would do, field training exercises and put those little things on everybody and on the helicopters and everything. And he said, if you shot at the sensor on the back of the helicopter, close to where the rotor was, it would go off. And it's like, oh my Lord, he shot the helicopter down with an M16, Well, can you do that? Well, yeah, you could. It'd be a heck of a shot, or unload a clip or two if you have time. Of course, they're shooting back. And, you see that stuff in the movies and you wonder, is some of it real, some of it not real? Well, some of it's way exaggerated, but... Yeah. Yeah. Unless it's an Apache or something. Now, those are pretty rugged.
The force of the rotor is pushing down.
Mm-hmm.
The amount of air coming off this.
Mm-hmm.
Yeah. That's why it's hard.
That's why it's like shooting down.
Yeah. Yeah.
A small caliber.
Yeah.
Because the thing when they land,
Yeah.
the rotor launch is...
Yeah. They kick up a lot of... Yeah, and that's true. Yeah. That's a good point. Yeah. Yeah. But you got to have that back rotor to balance it. Okay. Got to. If it ever gets out of sync, we're in trouble. Something happens to it. I know a guy I went to school with works for the Arsenal, and he told me, he said, good Lord, I think I told y'all this, that he's surprised at how some helicopters especially can even fly. But they do. They really do. And the resistances and tolerances that the government allows. So he said, I just not too crazy about flying. But anyway, okay. And then angular momentum. Now, so we take torque. Now here we take angular momentum L. That's the unit right there, L. So you have an object in motion. Notice we've got the mass times the radius squared, which is what? The moment of inertia. Mass times the radius squared is the moment of inertia. Okay, and I'm on page Yeah, where are we? Page 317, angular momentum. And so we take the mass radius squared times the angular velocity and gives us angular momentum. So how does an object, how does that top spin? How does it stand up? We apply a tangential force to it, by the way. If you've ever noticed how you wrap the string typically around the edge of the top, I wished I had one to demo, and then you pull it and spin it, you're actually applying a tangential force to it, okay? You're applying a tangential force across its radius, which is torque. You're giving it torque, okay? And so we also give it angular velocity. It causes it to stand straight up, doesn't it? It's pretty unique, too, because the force and the torque is this way, but the top stands up this way. You ever notice that? You apply the force, the torque, in this direction, but the object stands up vertically, horizontal to vertical. That's why we call it angular momentum. And two, because it's through the displacement of, it's through angular displacement. Okay? Okay. I don't know if you've ever, and I used to have the angular momentum device, the bicycle wheel with the two handles on it, and I do not know what happened to it. I cannot find it. I got to find it. I've not been able to find it. We had one, and when we remodeled the building, did all the mildew stuff, a few things disappeared. So I need to find it. But it's pretty unique. I don't know. You may have demonstrated this in high school. You could sit in a chair, a chair that would spin real well, like a stool with that spun real well. Or these chairs would probably do it. They're lubricated fairly well. But you could hold the bicycle wheel and and it was a hard rubber bicycle tire, and spin it, and then you could torque one side or the other, and whichever way you moved your hands, if you moved your hands to the right, the chair would spin to the left. Or if you moved them to the left, the chair would spin to the right, or you and the chair would spin to the right. It's pretty neat. And again, that demonstrates conservation of angular momentum. And Newton's third law, too. Because with every action, there's an equal and opposite reaction. So it's a good little demonstration. Man, I wished I could find it. Anyway, so I may just have to get a new one, heaven forbid. But, anyway, maybe somebody didn't steal it. Okay. So again, angular momentum, the moment of inertia, as I was just showing you a minute ago, times the what? Angular velocity. So there's your equation. And, of course, the units for momentum is what? The units will be what? Well, it's kilograms. Remember now, moment of inertia is kilograms what? Meters squared, and then we've got what? We've got radians per second. So our units for angular momentum is going to be what? Kilograms. So we got what? We got kilograms, meters per second. Is that right? Kilograms, meters squared per second. Right? That's the units for angular momentum. Is that correct? Look at your units. A moment of inertia is kilograms, meters squared, and angular velocity is radians per second. So it had to be that. Kilograms, meters squared per second. Okay, so that's the units for angular momentum. Okay. All right. And yes, we can find the torque if we take the derivative of the angular momentum. So basically we go backwards, don't we? We can find the torque from angular momentum. Okay? All right. And I think that's it. Now, as I said a minute ago, conservation of angular momentum, provided that the net torque on a device, on an object, is zero, then what? then momentum's conserved. Now, if you apply more external torque, then you change the angular momentum. But if the net torque on a device is 0, then the angular momentum is conserved. Now, here they show us the right-hand rule again, and notice too, this is what I was talking about earlier. All right. Notice how the angular velocity and the angular momentum are in the same direction. So when their vectors are parallel, when they're parallel to each other, you've got what? You've got positive angular momentum. You've got negative angular momentum when they're, and of course that's counterclockwise, when they're clockwise, right? And of course if one was in the opposite direction, if they were anti-parallel, opposite directions, then you would what? You would have negative, right? Okay. Opposite directions? Okay. All right. Now, earlier we've been looking at what? We've been looking at the torque. Now, where are we applying torque? Well, we're applying the tangential force. If, let's say, that was a top, we would have been applying that right there, wouldn't we? So the force is actually applied this way, but the momentum is that way. Okay, it's perpendicular to the direction. It's perpendicular to the direction of the applied force, isn't it? Force is this way. Angular momentum's this way. Perpendicular, isn't it? Okay. Okay. All right. And that would have to be the relationship between angular momentum and angular velocity. There would have to be a cosine relationship, wouldn't it? Cosine of 0 is 1. Okay. It'd have to be cosine, wouldn't it? Okay. All right. Any questions?